Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain shear stress and associated shear strain caused by the shear stress. All of you know that stress is the internal resisting force exerted by a material per unit area against external loading. If the resisting area and the load are mutually perpendicular, the corresponding stress induced is normal stress. Now another type of stress which we come across in the loading is shear stress. So if the resisting area is parallel to the load, then corresponding stress induced is shear stress. So in the figure I have shown a riveted plate. So two plates are riveted using a rivet. Now loads are applied at the ends of the plates. Now in this case, in the plate, the area which resists the load is normal to the load. So if you take the resisting area and load are mutually perpendicular. So the plate is subjected to normal stress, and since it is a pull on the plate, this pull is acting towards right, and force on the left side is acting towards left. So this is pulling the plate. So this force acting on the left side will be transmitting to this lower plate through the rivet, and it will be exerting a force towards left. So the lower plate is subjected to tensile force. So it is subjected to normal stress. Similarly, the force applied on the lower plate will be transmitted to the upper plate through the rivet, and force will be acting towards right, and this plate will be subjected to tensile force. So both the plates are subjected to normal tensile stress. Now let us take the case of a rivet. On the rivet, the plate is exerting a force on the rivet towards left, and this lower plate is exerting a force towards right. Now the rivet is resisting this force P, and this force P is acting and which is trying to shear the rivet. So on the rivet, two forces are acting. One is towards right and another towards left. And the cross section of the rivet, that is the area which resists these forces, is parallel to the forces. So the resisting area and forces are mutually parallel, and they are lying in a horizontal plane. So the corresponding stress induced is shear stress. So the rivet cross section is resisting these shearing forces, and you can find out the shear stress as force P divided by the area which resists that load. It is pi by 4 d square, where d is the diameter of the rivet. So you can find out the shear stress as again force divided by resisting area, but resisting area is going to be parallel to the load, and whichever area is resisting that load, you have to take that area into consideration in the calculation, and you denote the shear stress by the notation tau. So that calculation I shown here. When you take the rivet, the shear stress induced tau is force is in this case is P. Force acting on the rivet is P divided by resisting area is area of the cross section of the rivet, which is pi by 4 d square, which will give the shear stress induced, and the notation used here is tau. Unit of shear stress is also Newton per mm square. Now we will consider another example, the punching of a plate. During this process, the plate undergoes shear stress. Now the punch is acting on this. Now the small portion which is removed is shown here. Now the force is acting vertically downward. Now the resisting areas inside the plate, this portion is removed. using the punch. So the area which resists this force on the punch is inside portion of this plate. So that removed portion I have shown here, and this colored portion, red colored portion, is the area which would have resisted that load against shear deformation. The force is applied, so this inside area which I have not shown here, okay, inside area you cannot see here, but this removed portion you can see this red colored portion, that is the inside area which would have resisted the applied force. This area is lying in the vertical plane, and the force is also vertical, and both area and resisting area and force are parallel, and the corresponding stress induced is shear stress. So the punch is shearing the material plate, shearing the plate, and corresponding stress induced is shear stress, and you can find out the shear stress as force by resisting area or shearing area. So in this case force is P, and the area which resisted is, to calculate this area you can calculate the circumference of this into thickness of the plate, that will give the resisting area. So pi d into thickness, so that will give the resisting area. So tau is equal to, shear stress is equal to force divided by resisting area, P by pi dt. So that will give the shear stress applied on the plate, or shear stress offered by the plate. Now this shear stress induces strain in the material. The normal stress induces a strain, and that strain is called normal strain, and correspondingly you have normal tensile strain and compressive strain. So in case of shear stress, it induces a shear deformation, that is called shear strain. So it is a angular deformation of a material when subjected to shearing force. The shear force applied on a material produces shear deformation. The angle through which the material is deformed is known as shear deformation or shear strain. Consider a block fixed at the bottom end and subjected to a shearing force at the top. So this will cause a shearing force, because resisting area is going to be parallel. This is a resisting area parallel to AB. All these sections are resisting this applied force. If any of the section is weak, the material will shear. Okay, so it can also rotate, and it causes bending. Along that, it can also cause, if the material is weak in shear, it can shear off. So this applied force, if a material is not failing, so sometimes it without much shear deformation, it can shear into pieces. But if material undergoes deformation, it will rotate through an angle. This point A moves to A1, and D, since it is fixed, it remains there. So there is a deformation. So this fixed end will be exerting a force in the opposite direction, because it's this force, to balance this force, this fixed end will be exerting an opposite force, and that causes a shear deformation, and the angle through which it turns is known as shear strain. That's phi in the figure is a shear strain. Now you can find out shear strain phi like this: AA1 divided by AD, that will give the tan of this angle, or tan of shear strain. So tan phi is equal to AA1 divided by AD, or AA1 is also equal to BB1. So this is also shear strain. BB1 by BC is also shear strain. Since phi is very small, so the shear deformation is going to be very small, you can take tan phi is equal to phi. So whenever the angle is very small, tan phi and phi are equal. So shear strain, instead of tan phi, you can write phi. Phi is going to be AA1 divided by AD or BP1 divided by BC. So shear strain phi you can calculate like this: AA1 divided by AD. So that is the shear strain induced in the this case. That's all for today. Thank you for watching.